This is for AP Physics 1, and this is in addition to, this is in your electrostatics packet, and this is over Coulombs law. So there should be a space as well as the examples that we can work on. Remember again, if any of this needs to be paused, it can be. All right? So let's talk basically about Coulombs law. Coulombs law says that 2-point charges exert a force on one another that is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between their centers. This equation is on your formula chart, and it's F equals K Q1 Q2 over R squared. This should look very, very similar to our F equals G M1 M2 over R squared formula. And that's because they are very similar formulas, but instead of talking about masses, we're now talking about small particles like electrons. So we're talking about their charges, and instead of using the universal gravitational constant, we're using what's called Coulomb's constant. That's our K value. And instead of talking about the distance between the two mass centers, we're talking about the distance between the two charges centers. So F does stand for your electrostatic force, and it'll still be in the units of newtons. Q is now going to stand for charge, and it's going to be in the units of coulombs. K is going to be 9 times 10 to the 9th. And the units for that are Newton meters squared over coulombs squared, which actually, when you look on your formula chart, it's a little bit different than that. No, actually, it's exactly like that now. It depends on which way you look at it. But it does have it as 9 times 10 to the 9th Newton meters squared over coulombs squared, which it hasn't always been like, but it is. And then R is going to be your distance of separation between the charges, and that's going to be in meters. Now you'll notice on your formula chart that even though the force is a vector value, that we use the absolute value for it. So it doesn't matter whether the charge is positive or negative, it's still just going to be the absolute value. So we're just going to use the magnitude of the charge, not the sign of the charge. So that'll be important later on. The other thing to realize is when we're dealing with electrostatic force, remember that I have said that a force is a force is a force. And remember when we said that centripetal force could be our gravitational force? So we can set some equations equal to each other again. So just be aware that that'll be able to happen. But these forces, these charges, are going to be exerting an equal and opposite force on each other. So that's why we put both forces in, or both charges in the formula. So the value of K can be expressed in terms of the permeativity of free space, and it's an epsilon naught. Believe it or not, this, and that was on the recording, not actually in class, ladies and gentlemen. Okay? This isn't on your formula chart so much, but it is on the, it does show the 1 over 4 pi epsilon naught, which comes out to be the same value. We actually talk about it more in AP Physics 2 than we do in AP Physics 1, but I just wanted you to realize that it does have something to do with it, because K is proportional. K is used primarily when we're talking about air, and everything we do is in a vacuum or with air, and so our K value is always going to be 9 times 10 to the 9th. But if I use something besides air, the value would be a little bit different, because that would be called a dielectric, and that would cause the charge to not be able to move through the medium as well. Again, that's on the recording, not in class, so make sure you're paying attention. That's on the that's on the recording, not in class. Class is not over yet. Don't go anywhere. Okay. All right. But again, we'll talk more about this when we're talking about, like I said, in AP2. So unless you're taking that, you won't really have to worry about this too much. All right. So let's talk about an example problem, and you should have this in your notes. All right. So I have my little guy here with his balloons, and if each of these balloons is 2 times 10 to the negative 6, and they are 0.7 meters apart, I want to know what the electric force or the electrostatic force between the two balloons is. So I'm going to go ahead and first write my variables. I know that Q1 and Q2 are both 2 times 10 to the negative 6 coulombs. I know my D value or my R value. I sometimes write it as D, so you might see it as K Q1 Q2 divided by D squared. So just FYI, because I kind of look at it more as a distance between the two, because R has been used for radius and other things, so I typically use D, just so you know. So if our formula is F equals K Q1 Q2 over R squared, and both our Q's are the same value, then we can just square our Q value. So we would have our 9 times 10 to the 9th, Newton meters squared over Coulomb squared, multiplied by our 2 times 10 to the negative 6 coulombs squared, because each one of the Q values was that, divided by the 0.7 meters squared. Again, don't lose the squares. So the meters squared on the bottom, and we'll cancel out with the meters squared in our K constant, and then the Coulomb squared will cancel out with the Coulomb squared in our K constant. So you'll end up with only the newtons left over with your 9 times 10 to the 9th value, and that's why your answer is going to be 0.073 newtons. Okay? So, pretty easy problems. Like I said, they should really remind you of our universal gravitational force problems that we did, so as you're working through those. So, the next question would be, is this an attracting force or a repelling force? Well, if you remember, our electrostatic laws say that like charges will repel each other and opposite charges will attract. So both of these were charged 2 times 10 to the negative 6 coulombs. So they're both positively charged. So this one should be, which one? Attracting or repelling? Come on, somebody should answer me even though I'm not standing here. All right, hopefully you're saying repelling. They should be repelling force. Okay? Moving on. Example 2. Oh, look, I put hearts because it was just after Valentine's Day. All right, we have 2 equally charged balloons, and they are going to repel each other with a force of 4 times 10 to the negative 3 newtons. If they are 0.015 meters apart, what is the charge of each of the balloons? So, we have our force value, we have our distance value, so we will need to take our original equation of our F equals K Q1 Q2 over R squared and rearrange it. And if we are now looking for those charge values, then we can say that Q squared is F D squared or R squared divided by K. And then we'll have to take the square root of that. So we'll take 4 times 10 to the negative 3 newtons multiplied by our 0.015 meters squared, divided by our 9 times 10 to the 9th, Newton meters squared over Coulomb squared, and then we'll have to take the square root. Don't forget to take the square root, okay? And then you should end up with both the charges being 1 times 10 to the negative 8 coulombs. All right? Hopefully, I think we have one more. All right, one more. So if the two charges are, Q1 is negative 8 microcoulombs, and Q2 is 12 microcoulombs, and they are placed 12 millimeters apart in the air, what is the resultant force on the third charge, which is Q3, which is a negative 4 microcoulombs, placed midway between the other two? This is where you have to think about the fact that we're going to line them up like this, and we're going to have a negative and a positive on the end. So, again, that is not your bell. Sorry, I am having to record through the bells here. Alright? So, I'll pause it so we don't hear the other one. Alright, so now we won't have to worry about any bells. When I put a negative charge in the middle of these, the Q3 value is going to be pushed away. It's going to repel from the Q1 because those are like charges. and then the Q3 is actually going to be attracted to the Q2. So when we look at these as force values, we're going to have our charges of Q1, Q2, and Q3. And by the way, to change from microcoulombs to regular coulombs, you will just take that number and do times 10 to the negative 6. Okay, so that's how to get from micros to regulars, just to let you know. And you can also find that as a prefix on your formula chart for micros, that it is 10 to the negative 6 micros, or in a base unit. So that's why you would just multiply it by times 10 to the negative 6. All right? So if we know our radius value is 0.12 meters, because we have to change it from millimeters to meters, then it's put it halfway in between. So now we know the distance between 1 and 3 is 0.06, and we know the distance between 3 and 2 is 0.06. Okay? So we need to find just the force between Q1 and Q3, which will be pushing Q3 away. So that's why I have it as a vector arrow that direction. And then for F2, I just need to look at Q3 and Q2, which will also be going that way because Q3 is going to be attracted to Q2. Now, since these are vectors and they're in the same direction, okay, then we will add these two values once we find them. If they had been going in the opposite direction, we would have gone ahead and subtracted them. If they would have been going at an angle, then we could have found component forces. I know you really liked hearing that, by the way. I know you were super excited. So we want to find the overall force between them. So we want to find that resultant force. So we're going to start with our base formula of F equals K Q1 Q2 over R squared. Now we're going to start with first F1, and F1 would be our K value, and then we would have Q1 and Q3 that are involved because we're talking about just those two charges. And they are 0.06 apart. Don't forget to square those. Again, I converted from micro to regular coulombs by doing times 10 to the negative 6. And I would come up with a value which ends up being 80 newtons. Remember, we don't include the sign. The sign was there to help us determine direction for the force. Okay? Then for F2, I'm going to use Q3 and Q2's values, just their magnitudes, converted from microcoulombs to coulombs, and the distance between them was 0.06, since I put Q3 right in the middle. So that gave me 120 newtons. So to find my overall, my resultant force, I would just add the two together, and that would be 200 newtons to the right, or towards Q2, because everything's going to go that direction. All right, we'll talk more about components and things when I'm back in class, but hopefully this gives you a little taste of what we can do with more than one particle. But remember, the formula only has two charges in it, so we can only talk about two particles at a time. And then we can create forces, and then we can deal with resultants. All right? You guys work hard on your class worksheets. They are two green sheets of paper that you need to do on your own piece of paper. And turn in what you complete by the end of class. Have a great day.